Okay, so in our last class, we covered simplifying radicals. Here, what we're going to be doing is first adding and subtracting, and then multiplying radicals as well too. So radical expressions are not just of one term. There can be multiple terms separated by addition and subtraction signs. So we need to know how to deal with the addition and subtraction of radicals. So this is termed in this blurb here to be the addition property of radicals, but this is really addition and subtraction. So it's a root b plus or minus c root b is equal to a plus or minus c quantity root b. So what that essentially means is that to add or subtract radicals, the index and the radicand must be the same. Now, index, that's a new phrase and a new word that we haven't seen before. All the index refers to is that the index is for a square root 2, for a cubic root 3, for a fourth root 4, etc. So in the same way that we can undo squares by taking the square root, you can undo, let's say, 3 cubed by taking the cube root. So I'm just going to just get that on the side here. This is not something that we'll be dealing with entirely at all, I should say, for this work, but it's something that's good to know and you should know. And going on here, so if I were to have, for instance, 2 cubed, right, that's equal to 8, I can then, in the same way that I'm taking the square root, I can take the cubic root. The index is up here, right? Right on the top of the radical sign. If I take the cube root of 8, that's equal to 2. So the cube root undoes cubing the same way that the square root undoes squaring. And note for the index for squaring, like for instance the square root of 4, we don't write the 2 here, but it's implied that the index of a square root is 2. So that's what they mean when they say index. We're going to be working with only square roots, so the index automatically is going to be equal. So that's more of a side note. But essentially, the index and the radicand must be the same. So what does that mean? You can think about this essentially as being like terms. In that, and in fact, this is how you should think about it. So in my little thought bubble here, I'm saying, like terms, quote unquote. So in the same way that we have like terms involving variables, for instance, x and 2x, right? These are like terms. We can add them to make 3x. However, we cannot add x and 2y. These are not like terms, right? X plus 2y is already in simplest form. So in order to add, let's say, for instance, here in this work, 3 root 5 plus 7 root 5, the only reason why we can add these two is because they both have a root 5. So these can be considered, quote unquote, like terms, although they really are the same radicand. That's officially how we should think about it. So what do? In the same way that we saw that it's a plus b, the quantity of a plus b, all that means is that you just add the coefficients. So this is simply just 3 plus 7, so I'll write that in here. The quantity of 3 plus 7 root 5, which is simply 10 root 5. So easy enough. I'm sure given a million problems and just seeing that one, every student in the class could get this right. So along the same lines, 10 root 3 minus 4 root 3 is just simply 10 minus 4 is 6 root 3. Okay. So let's take a look at this example. Now we have multiple terms, but note that the radicands of root 5 and root 5 over here, root 3 and root 3, the first and third terms can be added, and the second and fourth terms can be added, or in this case subtracted, but they can't be combined together. So if I add the root 5s together, I get 8 root 5, right? And then I add the root 3s together, 8 subtract 3 is plus 5 root 3. So my final answer, once I've combined the 5s, 2 root 5 and 6 root 5, and then combine the 3s, 8 root 3 subtract 3 root 3 is 5 root 3. So my final answer, 8 root 5 plus 5 root 3. So it's possible to have an expression that has 4 radical terms in it and then combine down to 2, combine down to 3. You can have an expression that has 10 terms that goes down to 8, down to 1, et cetera, et cetera, et cetera. All right. Now, you're not always going to have these clean radicands that don't need to be simplified. No. In fact, shocking, we need to combine the work we did on day 1 with this work. So root 27 can be simplified. I'm going to keep 3 root 3 because that's fully simplified. But root 27, we need to think about that as what is the largest perfect square factor of 27. Turns out that that is, of course, 9. So this simplifies to 9 root 3. And then we can think about this as 3 root 3 subtract, and I'll put this in brackets, root 9 times root 3. We can simplify what's in the brackets, keeping the 3 root 3, of course, to root 9 is 3, so that's minus 3 root 3. It turns out that I'm subtracting 3 root 3 from 3 root 3, so my final answer is 0. Because if you want to think about this as subtracting the coefficients, 3 minus 3, 0 root 3 is still just equal to 0. So my final answer here, 0. Okay, let's try this one. Negative root 12 plus 3 root 3. That is, 3 root 3 is fully simplified. Negative root 12 is not. So root 12 can be simplified to root 3 times 4 plus 3 root 3. This is negative, and I'm doing this as root 4 times root 3. When I split it up into 2 radicals, still keeping plus 3 root 3 on the end here. So this is negative. The root 4 turns into 2, the coefficient. I keep the root 3. Negative 2 root 3 plus 3 root 3. Negative 2 plus 3 is just 1 root 3. But in the same way that we don't write 1x, no, 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 we don't want to write that. 1 root 3 is just simply termed to be root 3, my final answer. Okay, so a couple of your term problems, try those out. You will need to simplify some of the terms in, potentially, I'm not saying you will or you won't, but potentially you will need to simplify some of the terms in this B problem. You'll have to find out and think critically about it. Can I simplify any of those terms? Okay, now we're learning how to multiply radicals. So this is very simple and intuitive, the same as adding and subtracting. In that, if I have a root b times c root d, my result is simply just the coefficient is the multiplication of the coefficients, in this case a times c, and then inside the radical, in the radicand, is just simply the multiplication of the 2 radicands, b times d. So this is turned on the bottom here. So multiply radical expressions. The index must be the same. So once again, our index will be the same because we're dealing with the square root in every case in this unit. And then you find the product of the coefficients and the product of the radicands, and then just you simplify the expression. So once you find the product, there's a pretty good chance that you'll have to simplify because the result in the radicand will most likely have a perfect square factor. So let's see a example of that. So let me just get my trusty pen out over here. Okay. All right, so we have 3 root 6 times 4 root 5. The multiplication of the coefficients is 3 times 4. So I'm going to be very clear about this. I'll put that in parentheses. Square root of 6 times 5. So that follows very clearly. This is just simply a times c. That's the coefficients. B times d, that's the multiplies to be the radicand. So what happens when we multiply these out? This ends up being 12 root 30. Now, I didn't simplify 6 and 5, or 6 times 5, because neither of them are perfect squares. I need to multiply these 2 products underneath the radical or in the radicand to be 30 to understand if I have a perfect square factor of 30. So I think to myself, are there any perfect square factors of 30? And you should, at this point, start to think about memorizing the perfect square. So I'm thinking to myself, in my head, when I try to think if there's any perfect square factors, 1, of course, we don't deal with. I always start with 4. Can 4 go into 30? No. 4 times 7.5 is 30, so that's not going to work. 7.5 is not an integer. 9. Does 9 go into 30? No. Does 16 go into 30? No. Does 25 go into 30? No, 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 no. It turns out 12 root 30 is a final simplified answer because the square root of 30 is fully simplified radical expression. There are no perfect square factors of the square root of 30. Next one, we might not get so lucky this time, perhaps. 2 times 3 is 6. 10 times 6 is 60. I think we dealt with root 60 today in class, possibly. Square root of 60. So once again, I'm starting with 4. Is 4 a factor? Yes, but I want to continue on just to make sure I don't have any other factors that could possibly be larger, so I don't have to continue to simplify. Is 9? No. Is 16? No. Is 25? No. Is 36? No. 49. Okay, then once I get to 49, I know that half of 60 is 30, so the factor pair at least has to be 2. So once I get up to 49, I know there's no other numbers I need to deal with because I know for sure that 49 is greater than 60 divided by 2. So once again, basically that follows this logic. If 49 is a factor pair, then 2 and 49 have to be at least what I'm dealing with. But 60 is less than that. That ends up being 98. And of course, 98 is much greater than 60. So 4 is the perfect square that we're dealing with. So I keep 6 root 60, except I convert 60 into 4 times 15. I convert that to 6 times root 4 times root 15. And then 6 times root 4 turns into 6 times 2 times root 15. 6 times 2 is 12. Root 15 is my final. Whoa! That totally made a really weird line. That looks like a huge spike in a wave. I don't know what that is. Ignore it. Final answer, 12 root 15. I'll write it down just for clarity. 12 square root of 15. Okay. All right. So your term problems A and B, try those out. This is relatively intuitive. We'll be doing some practice work and then some extension work with this in class on Wednesday. Have a nice day.